Tonight, the solar system held its breath. A mysterious interstellar visitor named 3IAtlas passed just 28 million kilometers from Mars, so close that every Mars orbiter raced to capture its secrets. But Earth was blinded by the sun, leaving only our robotic explorers to witness what may be the strangest comet ever seen. Glowing emerald, pulsing like a heartbeat, and moving with precision that defies all known physics. Was this a natural comet, or something far more extraordinary? Stay tuned, because what these orbiters saw could change everything we think we know about visitors from the stars. As the countdown reached 0, every eye, human and robotic, turned toward the red planet. It was more than just a scientific observation. It was a moment where humanity collectively held its breath, waiting to see whether this interstellar object would reveal natural cometary behavior, or whether its mysteries pointed toward something far more extraordinary. Just as 3IAtlas raced toward its closest approach to Mars, Earth itself was forced into silence. This was not because of a failure in our telescopes or a technical breakdown. It was simple geometry. The sun moved directly between Earth and the red planet, creating what astronomers call a solar conjunction. For nearly 6 weeks, ground-based observatories and even powerful space telescopes like Hubble and James Webb were blinded, unable to track the interstellar visitor. This blackout meant that during the most critical hours of observation, Earth was no longer the center of the story. Instead, Mars took on the role of the solar system's only outpost capable of keeping eyes on the object. In those hours, a handful of orbiters circling Mars became the world's last link to the truth about 3IAtlas. If you're fascinated by mysteries like 3IAtlas, help us keep uncovering the unknown. Hit that subscribe button and join our growing community. Your support keeps us going, inspires new content, and truly makes us happy to continue this journey with you. The MAVEN spacecraft, Mars Express, and the ExoMars Trace gas orbiter were pushed into emergency observation campaigns. Each was programmed with special routines, operating at the edge of their power and data limits. These orbiters were tasked with catching every detail: the color and chemistry of the coma, sudden flares or breakups, even tiny course changes that might betray hidden forces at work. While Earth went dark, mission teams shifted into overdrive. Control rooms across the globe synchronized with one purpose: keep the data flowing, no matter what. For those 6 hours, the survival of the mission rested on Mars alone. It was as if the universe had pulled a curtain across our home planet, forcing us to rely on distant robotic explorers to uncover whether 3IAtlas was a comet, a cosmic oddity, or something altogether beyond imagination. As Mars orbiters locked their instruments on 3IAtlas, one of the first revelations stunned even veteran comet scientists. Surrounding the object was a glowing emerald green coma, so vivid that spectrographs from multiple instruments confirmed the strange hue. Normally, comets glow faintly with the familiar signature of water vapor, carbon monoxide, or faint cyanogen bands. But this was different. The intensity of the green light simply didn't match anything ever seen in the solar system. The chemistry of the coma added an even deeper layer of mystery. Instead of water dominating the emissions, as it does in virtually every known comet, the spectrum of 3IAtlas revealed an overwhelming presence of carbon dioxide. The ratio of CO2 to H2O wasn't just unusual, it was extreme. 8 parts carbon dioxide for every single part of water vapor. That is an order of magnitude higher than even the most volatile rich comets we've ever studied. Laboratory models have struggled to account for this fingerprint. Even the coldest, most distant objects from the Oort cloud have never displayed chemistry so skewed. Some researchers suggest it points to 3IAtlas having formed in an environment radically different from our solar system. Perhaps in the deep freeze of interstellar space, far from any parent star. Others whisper about possibilities beyond natural origins, Could such a precise and stable ratio be the product of something engineered, a sign of an alien process at work? The emerald glow didn't fade. Across instruments and across wavelengths, the light held steady, defying conventional explanations. Every reading only deepened the sense that this object wasn't playing by the rules. Whatever 3IAtlas truly is, its chemical fingerprint may be the most alien evidence humanity has ever recorded. If the emerald glow and unusual chemistry of 3IAtlas raised eyebrows, its behavior in motion set off alarm bells. From the very first telescopic detections, astronomers noticed a rhythm in its brightness. Instead of random flares, like a normal comet jetting gas and dust in chaotic bursts, 3IAtlas brightened and dimmed with astonishing regularity. The pulses came like a heartbeat, sharp spikes of light, clean rises, clean fades, repeated again and again with almost mechanical precision. This strange rhythm was first spotted by a citizen astronomer in Pune, India, who tracked the light curve through her backyard telescope. At first it seemed too unusual to be real, but professional observatories soon confirmed it. Even as the object drew closer to the sun, through glare and interference, the periodic pulses remained unblurred and unwavering. Even more unsettling was what came next. Alongside each pulse of brightness, the orbit of 3IAtlas shifted ever so slightly. Tiny microaccelerations, as if the object were nudged or corrected, were measured by astrometric trackers. The timing was uncanny. Each surge of light perfectly aligned with a course adjustment. For natural outgassing, this is almost unheard of. Comets vent in unpredictable directions, producing jittery, uneven motions. But Atlas moved as though someone, or something, was steering it. Individually, these anomalies might be explained away. But together, synchronized light pulses and corresponding changes in trajectory painted a picture of control, not chaos. Scientists were left with a chilling question. Was this interstellar visitor simply a comet, behaving in ways we don't yet understand? Or had we just witnessed the first hints of something engineered, a machine masquerading as a natural body? With Earth's telescopes blinded by solar conjunction, the entire burden of observation shifted to Mars. Orbiters and rovers became our surrogate eyes, executing one of the most ambitious interplanetary observation campaigns in history. Unlike typical comet flybys, this effort was anything but routine. Mission planners at NASA, ESA, and Roscosmos coordinated down to the minute, issuing rigid protocols to maximize every second of the 6-hour window. MAVEN locked its spectrometers on the coma, scanning for isotopic fingerprints that might betray unusual chemistry, or even artificial compounds. Mars Express pointed its radar and plasma instruments outward, listening for strange disturbances in the interplanetary medium as Atlas passed. Meanwhile, ExoMars TGO performed continuous high-resolution mapping of gas release, searching for patterns that might confirm or dismiss the theory of engineered propulsion. Even the rovers on the surface, Curiosity and Perseverance, were ordered to look up. Their sky-facing cameras were calibrated to capture faint changes in the Martian atmosphere. If Atlas had fragmented or shed exotic material, dust signatures or chemical fallout might have rained down through Mars's thin skies. These rovers, normally focused on rocks and soil, became silent sentinels, recording every flicker of light, every trace of anomaly. The coordination was flawless. Data streamed back to Earth in bursts before communication blackouts began. Engineers knew they had only one chance, no second passes, no repeats. Every pixel, every spectrum, every radar ping mattered. And within those carefully planned observations, hints of something extraordinary began to emerge. Signatures that could not easily be dismissed as natural. Behind the scenes, mission control centers across the world entered a posture not seen since the Apollo era. Special contingency crews, nicknamed the Red Watch teams, were activated weeks before 3IAtlas's approach. Their mission was simple but sobering: prepare for the unknown. These teams rehearsed rapid response scenarios like military drills. What if Atlas suddenly brightened into a blinding flare, overwhelming instruments? What if fragments broke off, posing risks to Mars orbiters? And most unsettling of all, what if the object emitted signals, deliberate transmissions aimed at our machines? For each possibility, contingency protocols were written, tested, and rehearsed down to the second. Nothing was left to chance. Every data packet collected by orbiters and rovers was redundantly stored in multiple systems, transmitted along separate communication channels, and cross-checked by independent teams in real time. Even if one network went down, others would carry the stream. The stakes were too high for any glitch, any loss, any delay. Inside Mission Control, the atmosphere was tense but electric. Engineers knew they weren't just logging another interplanetary flyby, they were standing at the edge of a historic unknown. The Red Watch teams worked in shifts, eyes locked on monitors, headsets buzzing with constant crosstalk, as humanity's most advanced machines probed an interstellar visitor that seemed more mysterious with every passing hour. For these crews, the difference between routine science and a once-in-civilization event could come down to a single frame, a single spike of energy, a single anomaly in the noise. And everyone knew it. While space agencies coordinated fleets of orbiters and rovers, an equally critical effort was unfolding far closer to home. Across rooftops, backyards, and makeshift observatories, a global army of amateur astronomers turned their telescopes toward 3IAtlas. For many, this was the chance of a lifetime. The opportunity to track an object not from our solar system, but from the stars beyond. The first breakthrough didn't come from a billion-dollar spacecraft, but from a small observatory in Pune, India. An amateur astronomer there noticed something no one expected: a strange rhythm in the light curve. Faint pulses, dim to the eye but clear in the data, revealed a pattern. What began as a lone observation soon spread across forums and networks. Others checked, compared, and confirmed. The pulses were real. Soon, global citizen arrays, collaborative groups of small telescopes linked by shared data, joined the campaign. From Chile's high deserts to backyard setups in California, from Europe's clear skies to remote outposts in Australia, streams of real-time photometry and astrometry flowed together. These weren't just hobbyists. They became a living, breathing extension of humanity's sensor network, filling gaps when professional instruments were blinded by the sun. Their contribution was vital. While space agencies provided precision instruments, the sheer number and geographic spread of amateurs created an almost continuous chain of coverage, ensuring no anomaly went unrecorded. It was a reminder that discovery doesn't belong only to governments or institutions. Sometimes the first whispers of the extraordinary are heard not in control rooms, but in the quiet of a backyard observatory. In the weeks following the Mars campaign, scientists turned from observation to explanation. The extraordinary behavior of 3IAtlas had to be placed within the boundaries of natural science, or else. 4 main hypotheses emerged, each attempting to account for the emerald glow, the skewed chemistry, the brightness pulses, and the strange microaccelerations. The first possibility focused on extreme interstellar chemistry. Perhaps 3IAtlas had formed in an environment radically different from our solar system, far from any warming star. If so, its frozen ices and molecular reservoirs might be uniquely exotic, producing unusual chemical ratios and unexpected light emissions. This could explain the emerald glow, but the precision of the pulses remained troubling. Chemistry alone rarely keeps time. The second explanation looked at volatile gas pockets. Comets are known to hold buried reservoirs of carbon monoxide, methane, or carbon dioxide. If Atlas contained deep pressurized chambers, their release could, in theory, drive periodic outbursts. Yet, the consistency of Atlas's pulses, regular down to the minute, was unlike anything observed in outgassing events, which usually behave chaotically, not like a machine metronome. A third hypothesis examined unusual dust dynamics. Perhaps Atlas's coma was not merely glowing, but resonating. Dust grains interacting with solar radiation pressure could scatter light in strange, pulsing ways. But this idea struggled under scrutiny. Radiation pressure is constant. It doesn't produce sharp, timed bursts. And the linked microaccelerations, tiny nudges in orbit synchronized with the light pulses, remained completely unaccounted for. Finally, theorists pointed to gaps in our existing models. Maybe Atlas was teaching us something entirely new about cometary physics, revealing processes we'd never imagined. A natural event beyond current understanding. This was the most cautious explanation, one embraced by skeptics who warned against sensational claims. But here, too, problems arose. Models can stretch, but the data showed a precision and consistency that looked less like the messy chaos of nature and more like the deliberate pattern of control. None of these hypotheses fully held. Each solved part of the mystery, but left larger holes untouched. How could chemistry account for synchronized pulses? How could volatile release explain acceleration aligned so perfectly with light signatures? And how could dust scattering mimic the precision of a ticking clock? For every natural explanation tested, the same unsettling reality surfaced. The anomalies were too clean, too regular, too synchronized. What Atlas was showing us didn't fit comfortably within nature's toolbox. And so, behind closed doors, some scientists began to ask the unspoken question out loud. If it wasn't purely natural, then what was it? When the first streams of raw data from Mars reached Earth, the world held its breath. Every pixel, every spectrum, every radar trace could reshape humanity's understanding of what 3IAtlas truly was. But alongside the science, there was something else, a battle for trust. In past decades, claims of secrecy and withheld discoveries have dogged space agencies. Conspiracies thrive when data moves slowly, or when the public feels locked out of the process. This time, however, mission planners made a conscious decision. Absolute transparency. Agencies instituted strict chain of custody protocols. Every byte of data was logged the moment it arrived, time-stamped, authenticated, and duplicated across multiple independent servers. This ensured that no single laboratory, no single nation, could alter the record. At the same time, mirrored open archives were set up across continents, from NASA's servers in the US to ESA's databases in Europe, to repositories hosted in Japan, India, and South America. Within hours of receipt, compressed files of raw photometry, astrometry, and spectroscopy were made available to universities, amateur networks, and even the public. To reinforce credibility, agencies adopted rapid release policies. Instead of waiting months for peer-reviewed publications, preliminary findings, warts and all, were pushed online. If an anomaly appeared, it was visible not just to professionals, but to the citizen scientists who had helped flag Atlas's light pulses in the first place. The walls between professional science and grassroots observation began to blur. And yet, even with this unprecedented openness, doubts lingered. Forums erupted with debates over whether transparency was truly complete. Were there still classified channels? Were certain bands of the spectrum, radio or gamma, being filtered before release? The agencies countered with independent audits and real-time data feeds to reassure skeptics. The strategy worked, at least partly. Public trust soared compared to past missions, as ordinary people could download, graph, and analyze Atlas's strange signals for themselves. But the very act of releasing everything so quickly also amplified the sense of unease. Thousands of eyes across the globe confirmed the same troubling truth. The synchronized pulses, the microaccelerations, the emerald glow. These were not illusions of secrecy. They were real. Transparency had done its job. Instead of rumors and shadows, the mystery of 3IAtlas now stood naked in the light of public scrutiny. And that clarity made the anomalies all the harder to dismiss. As the dust settled after 3IAtlas's close flyby of Mars, the data painted a story both mesmerizing and unsettling. Scientists carefully combed through every spectrum, every image, every radar trace. Many of the features, the green coma, the carbon dioxide heavy chemistry, and even some aspects of the dust tail, could be modeled with natural explanations. But one thing remained stubbornly, undeniably unresolved: the synchronized brightness pulses and corresponding microaccelerations. These patterns defied all standard cometary physics. No combination of volatile pockets, dust dynamics, or interstellar chemistry could account for the clockwork precision seen in both light and motion. Every new analysis seemed to confirm one unsettling reality. 3IAtlas was not behaving like any natural object we had encountered before. Scientists could speculate, model, and debate. But the source of these signals, whether natural or engineered, remained a mystery. The encounter, however, left humanity with more than just questions. It forced a radical rethinking of how we monitor interstellar visitors. Protocols were rewritten. Data pipelines became faster, more redundant, and open to the public within hours, not months. Chains of custody, mirrored archives, and real-time citizen science collaborations became standard operating procedure. For future visitors from beyond the sun, the global space community was now prepared, coordinated, and transparent like never before. And yet, despite these advancements, the allure of the unknown persisted. Was 3IAtlas simply an extreme outlier of natural physics, a cosmic oddity from the distant reaches of interstellar space? Or did its mysterious pulses and microaccelerations hint at something far more extraordinary? For now, the question hangs in the void between Mars and the stars, unanswered but impossible to ignore. The flyby of 3IAtlas had changed everything, not just our understanding of interstellar objects, but the very way we watch, record, and interpret the universe. It reminded humanity that the cosmos still holds secrets beyond comprehension, waiting for those brave enough to look closely enough to see them. Want more mind-blowing cosmic discoveries? Click the video on your screen now and continue the journey through the mysteries of the universe.